Hello everyone and welcome back. Today we're going to start talking about angular physics. And in this video, I'm going to introduce two things. The first is going to be a unit that you're going to be using constantly. And second, I'm going to introduce three equations that are going to be extremely important when it comes to angular physics. But before any of that, I need to bring up an old friend, and that is the unit circle. If you're taking a physics class, then you are probably familiar with this to some degree. So I'm going to skip the basic introduction and get right to the point. Here is my circle. This distance is my radius. Now you may be familiar with this equation I'm putting on the upper right here. Circumference equals 2 pi r. This is an equation that allows you to get the circumference of a circle if you happen to know the radius. And the important thing about this is that it does not matter about what the size of the circle is. It can be really big or really small. It does not matter. This equation will always hold true, and I will tell you why. So this leads me to the true beginning of this video, which is what a radian is. So in your math class, you probably have been working with radians before, but after 20 years of teaching, I've found that not too many students can tell me exactly what a radian is or why it exists. So I'm going to fill you in on that little secret right now. Okay, as stated, this is my radius. I'm going to take the radius and I'm going to trace a path along the edge of the circle that is the exact length of the radius. I'm just going to eyeball it and I end up about here. Now, what is special about this is that no matter how large or small the circle is, if you take the radius and lay it out along the edge like you're laying down a piece of string, you will get this angle. And you will get that angle every single time. This length that I've traced along the edge actually has a name. It is called arc length, and its symbol is delta S. Now, if I were to keep going and I do a second length of R, I now get two of these angles. If I do a third length of R, I get three of these angles. So what's happening here is I'm forming a relationship that looks like this. Arc length over radius equals whatever this angle is. If I have three lengths of radius over here, then this angle is just 3. This, my friends, is what a radian is. Because here's the deal. If you look at the SI units, the SI unit for length is meters. The SI unit for radius is also meters. If I was to divide meters by meters, they cancel, which means this angle technically has no unit. It's obviously not degrees because 3 of them gets me all the way over to the side. However, if someone is asking you what the angle is for a measurement, you can't just say 3. Because the first thing they're going to ask is, well, 3 what? So the short story comes down to that they just made up a word, and they called it a radian. That's right, radian is a made-up unit. This is 1 radian, this would be 2 radians, and this would be 3 radians. However, that basically means radian is a fake unit. It does not exist. I'm going to tell you in a little bit why this is important. But the only reason why the word radian even exists is because it sounds really weird giving an angle with no unit. Now notice I have 3 radians. If I go a little farther and touch 180 degrees here, or pi, as you're probably familiar with, that would be about 3.14 radians, which is why pi even exists. If I keep going, and I now have 1, 2, 3, 4 radians, I end up about here. If I keep going, I'm now at 6 radians and I'm about here. And this little extra here is another 0.28 radians for a total of 6.28 radians for the full circle. This means if you take the radius and multiply by 6.28, you will get the circumference of the circle, which is exactly what our equation here is the upper right-hand corner. Which brings us to some pretty familiar equations. Circumference is 2 pi r. Area of circle is pi r squared, and volume of a sphere is 4/3 pi r cubed. All right, I'm going to move a few things around so we can chat and get to the point. Since this equation is simply the arc length divided by the radius is our angle in radians, it could also be written another way. All I have to do is multiply by r on both sides, and I have this. Arc length is delta theta times r. I'm saying delta theta because we're going to talk about an object that actually revolves. So if the object moved through an angle of 2 radians and you take that and you multiply by the radius, you would get an arc length that goes around the edge of the circle from start to about here. Same thing is true of 3 radians or 40 radians, etc. And again, if you do 6.28 radians, which is 2 pi, you will get the full circle or full circumference. So in other words, this little equation is something you may have learned in earlier grades, but that's not the actual equation. This is, because the angle could technically be anything. It doesn't have to be 2 pi. And if you've noticed, I've been saying 1 radian, 2 radian, 3 radian. It doesn't have to be in terms of pi either. That just makes things easier if you're doing half a circle or full circle or 3 circles or 10 circles or 1,000 circles around. Using pi usually means you're landing exactly on these points, but again, that doesn't have to be true either. While I'm here, this is a good place to talk about why radians is a fake unit. Let's say I have a radius of 4 meters. We're going to keep it simple. And we move through an angular displacement of 2 radians. You obviously would get 8, but you would get 8 what? Since you're talking about how far you've gone around the circle, this would be meters. You would not get radians meters. And that is because radians does not exist. It is a fake unit. Another way to put it is, if you multiply radians by anything, it gets eaten. It disappears. It is gone because it was never actually there in the first place. As another example we're about to talk about, if you had the unit radians per second and the radius was still 4 meters, in this case you would get 20. Again, meters gets multiplied by radians and radians is eaten. It is gone because it was never there in the first place. The important thing to note is that this equation allows you to convert from the linear variable of distance going around the circle to the angular variable of how much the object has turned in radians. And that's the important part. It has to be in radians. The actual name for this, by the way, is called angular displacement, or this is arc length, but it could also be called path length because it is the actual path a point would travel around the circle. All right, I'm going to move this, and we are going to do some derivations. First, I'm going to take this equation, and I'm going to divide both sides by time. And let's take a look at what we have. First, this would give us the unit of meters per second. How much path length you went around the edge of the circle over how much time it took. Well, meters per second is a velocity. It's a linear velocity. The only difference is that point or person or car or whatever is constantly turning a circular path, but it is moving a distance over a time. More accurately, it's a linear speed, but velocity is still the more typical term used. Now the new one is going to be this. If you take a look at the units here, you get radians per second. Well, that would be how many radians the object spins through per second. In other words, how fast it is rotating. This is called angular velocity or sometimes angular frequency. In the first few subtopics in angular physics, angular velocity is the term more commonly used. So that's the one I'm going to use for the rest of this video. The symbol is a little weird. The symbol is a lowercase omega, and it's this weird looking, not a W. I say not a W because it's not a W. It's a lowercase omega. Let me draw a little better. If you ever forget, just remember that the angular velocity symbol kind of looks like a pair of cartoon butt cheeks times radius because our radius is still here. This is actually the equation you will probably be using most often, with this one coming in second place. If you've noticed by now, velocity is all over physics. There's initial velocity, there's final velocity, there's average velocity, there's change in velocity. The same is true for angular velocity. There's initial angular velocity, final angular velocity, average angular velocity, change in angular velocity, same thing. And to go from one to the other, all you got to do is either multiply or divide by the radius. Now we're going to do one more. Only instead of velocity, I'm going to use change in velocity, which means I also have to use change in angular velocity. And again, I'm going to divide both of these by time. So this, if you say this out loud and you've been watching my videos, you should definitely know what this is. This is change in velocity over time. If you need another hint, the units are meters per second squared, which of course means that that is an acceleration. Again, it is a linear acceleration. It's as if a car was moving around a circular racetrack and was speeding up while it was doing it. On a side note, and I'll put it in to clear up that statement, these are also commonly known as tangential velocity and tangential acceleration. But the college world likes to use linear velocity and linear acceleration, so I'm going to keep using that term. The new one is going to be this. So if what we had on the left is linear acceleration, which is meters per second squared, this would be radians per second squared, which would make this angular acceleration, the rate of change of angular velocity over time. So if you, say, had a wind turbine or a fan that started at rest and then began to speed up, it would have an angular acceleration. Same thing would happen when you shut the fan off and it slows down to a stop. It would have an angular acceleration in the opposite direction. Speaking of direction, the unit circle says counterclockwise is positive and clockwise is negative. More on that later, but I thought I'd mention it now. The symbol for angular acceleration is known as alpha. And again, the radius doesn't go anywhere, so that stays here. All right, so take these three equations, put them in your notebook, box them, star them, circle them, do whatever you need to do to remind yourself that they are important. The reason they are important is because if you're going to translate from linear to angular, you must go through one of these three equations. They are basically translator equations. Meters to radians, meters per second to radians per second, meters per second squared to radians per second squared, or vice versa. In a first-time physics class, you're typically going to be using this one, and you're going to use it often. Second place is probably the arc length one, and third place, the acceleration equation. But you will be using them. All right, let's end this video with some definitions. First, arc length. The path traveled around the edge of a circle. The symbol is delta S, and the SI unit is meters. Again, it is literally how far you travel around the circular path. You can go a quarter around, half around, 3/4, or you can do multiple times around the circle, and it just adds up more and more and more and more and more. Second is angular displacement, and of angle an object rotates through. The symbol is delta theta. This represents how much angle something rotates through. If I have a door that you rotate or open from here to here, that would be an angular displacement of about 2 radians. Now, if I wanted to connect these two, I could say the length of the door is the radius, and I pick a point right at the end of the door here. I can then use this equation to find the path length that that point on the end of the door went through as it moved through the 2 radians. So the arc length will be this distance here in blue. Next up, angular velocity, also known as angular frequency, how much angle an object rotates through per unit of time. The symbol is a lowercase omega. And last but not least, angular acceleration, the change in angular velocity over a unit of time. The symbol is called alpha, and the units are radians per second squared. This is what happens, say, when an ice skater is spinning around and pulls her arms in and speeds up, but she speeds up rotationally. That is an angular acceleration because she increases her angular velocity. All right, I really just wanted to use this video as an introduction. The important things are knowing these 4 definitions, definitely knowing how to use these 3 equations, and having an understanding of what a radian is. If you can come out of this video knowing those 3 things, then you're off to a good start. In my next video, I'll get into more detail. Other than that, take care. This is Mr. M, signing off.